Welcome to module 3 of lecture 1. In the first two modules, we went over a discussion on why basic computer aided design is required in the VLSI design verification and testing process. And in module 2, we went through an overview of the entire design process. We understood that the design process goes from an initial specification of the behavior or functionality of an application to a finalized structure of a packaged chip. And this design process goes through a step-by-step process, and in this step-by-step process we go through a set of abstraction levels, and in each abstraction levels we have different views. We said that the important abstraction levels are the architectural level, the logic level, and the geometric level, and the important views in each of these levels are the behavioral level, structural level, and the physical level. Of course, in the architectural level and the logic level, the physical view is not particularly explicitly defined, but when the geometric level comes, we get an explicit view of the physical structure of the design. And then we also said that at each level the design progresses through stages, and the progress from one stage to the next, from a less detailed description of the design to a more detailed description of the design, this is called synthesis. And corresponding to the levels, we have three different important synthesis steps. One is the architectural synthesis, the second being logic synthesis, the third being geometrical synthesis or physical design. Now we will take a look at what these synthesis steps are. What are the important things that happen within each of these synthesis steps? Okay, just before going through the synthesis process, I would just like to iterate that the whole problem from the specification to the final implementation in the form of a packaged chip is essentially a single optimization problem. That optimization problem should take care of all issues relating to different aspects of the design and produce a final implementation or a structural output. However, this whole optimization problem cannot be solved in one step due to the sheer complexity of the entire design process, and hence people have divided the entire design process into split this design process into a set of steps so that the complexity can be reduced. Obviously, if you divide a single optimization problem into a set of steps, sub-optimalities will be introduced. However, to manage the complexity, this is the best trade-off that we have, and hence people over the years of research have found out these concrete set of steps through which the design flow should progress. So we come back to the original discussion that we were doing. So architectural synthesis is also called high-level synthesis. So the input to this is a behavioral model which can be abstracted as a set of threaded concurrent communicating process modules. So whatever we have been saying, we have said that this architectural module, the behavior will be its input, and it will be represented as formally as programs, right? So what will these programs represent? It will represent threaded concurrent communicating processes. So these processes will run concurrently and will communicate with other processes. And what will these processes represent? These processes will represent a set of operations and their dependencies. The process modules will have interfaces with other blocks and the outside world. So here we have 4 modules. So these 4 modules will perform 4 different functionalities. as we have found out, these are four different program codes, and these codes will run independently of one another concurrently and will communicate among themselves through these interfaces and can also communicate to the outside world. So this is what this figure shows. Now, how will architectural this architectural level specification, the input, be written in? So as we said, it will be written in hardware description languages like Verilog, systemc, VHDL, etc., or in architecture description languages. See, these architectural description languages are at a higher level. You can describe the pipeline stages, you can describe the structure of the ALU at a much higher level than the Verilog. The output of these languages will be another Verilog or VHDL code. So you can also describe using architecture description languages like Lisa, Expression, Mimola, etc. So at this stage of design, we can have two types of designs. We can have synchronous or clock designs or asynchronous designs. So as most of today's designs are synchronous, and it is much more mature than asynchronous designs. In the rest of this course, we'll only be taking synchronous designs into consideration. Step is to identify hardware resources that can implement these operations. Then we have to schedule the operations in different time steps. So scheduling the execution time of the operations. We have to schedule the operations at distinct time steps. And then we have to bind these operations to the hardware resources that we have identified. So the synthesis goes through these three major steps: identifying the hardware resources, scheduling it into time steps, the operations, and then binding the operations to the hardware resources. So what does synthesis define? So then synthesis defines the structural model of a data path. So why are we saying it a data path? As we said, the program will take some data as input, it will transform that data and will produce this transformed data as output after a set of transformations through the operations that I have stated. So this constitutes a data path, how the data flows from the initial input to the final output, right? So what this process will do basically will produce a structural implementation, a structural model corresponding to this data path. And how will this data path be realized? As an interconnection over resources, over the resources. What are the resources are? We are just coming to. And the logic, it will also produce not only this data path, but a logic level model of the control unit. So what will this control unit do? It will issue control signals to the data path according to the schedule. So what did we say? We said that we have a set of operations. These operations will be scheduled in a set of time steps. The data path will be realized. So these operations will be realized through a data path. The data path will have these operations and an interconnection among these operations. So these operations will be implemented through resources. By implementing these operations on resources, and there will be interconnections between these resources. Now, when we have a schedule of which operations to be excited at particular time steps, who will control which operations to be scheduled at which time steps? Because these operations are on resources, these particular resources which contain particular data at certain registers at a given time has to be activated as those instants of time, and therefore has to be controlled so that the correct data flows from the register to a functional unit and a correct output is produced and goes back to a register. I'll take this in more detail in the next few slides. So what we're basically trying to say is that the control unit will issue control signals to the data path according to the schedule. So it will control which registers, which functional units should be activated at each time step, so that the correct sequence of operations are performed according to the prescribed schedule. Okay. So we said the input specification to the synthesis process, we said what the synthesis process does, and then what will be the output of the synthesis process. The output of the synthesis process, as we said, is a data path and a control path. The controller design and the data path. The data path will be composed of what? A register bank, a functional unit bank, and an interconnection network. So I will have a register bank as the output. These will store the inputs to the operations at different time units. So these registers at different times can store different inputs. I'll take an example and explain, and then will these registers will be activated at appropriate instance of time, so that the correct data flows through the interconnection units to the functional unit, and the correct output is produced, and then it will again proceed through the buses to the register bank. So the register bank, the functional unit bank, and the interconnection network will form the data path, and it will also have the controller FSM that will control which registers / functional units to be activated when. So the registers, how we said there are registers, and how will they be controlled? How will this controller unit control as to what data should pass from the register when to which functional unit? How will this be controlled? It will be, the registers are connected to the functional unit via muxes. The mux is an N input, 1 output device. So therefore, what will it do? The registers float their outputs on the inputs of these muxes, and the output of the mux goes to the functional unit. So therefore, depending on which select lines are activated at what time step, a set of register outputs, right? So one of these register outputs will be taken from the input to the output of the mux, and therefore will flow to the functional unit, right? Similarly, the functional units are connected to the registers through demuxes. So why? Demux is again one input N output device. So the output of the functional unit now should go to a particular register. It cannot go to all registers. To a particular register where the output of this operation should legitimately reside. So therefore, the controller will appropriately select the particular output of the demux, so that the output flows from so that this output from the functional unit flows through the demux to the appropriate register, right? So therefore, the third point here is that the muxes and demuxes are controlled by an FSM. Now the design is therefore broken down into a set of clocked steps. At each step, some of the registers and functional units are activated, and these activations define the RTL assignments. So therefore, we have here two time steps shown. At time step 1, we have R1 equals to R2 into R3, and R4 equals to R2 plus R3. And in the second time step, we do R2 equals to R3 plus R4, and R5 equals to R6 minus R1. So therefore, there are a set of parallel register transfers at each time step. So this is the mathematical or logical output of the architectural synthesis phase, and the structural output being the realization in terms of registers, buses, memory, functional units, etc. Now at this step, because we have the parallel register transfers and the timing also specified for the circuit, The timing and other constraints can also be specified in the system through a set of temporal logic assertions, and hence we can verify that whether this design is correct with respect to the timing properties. That means, suppose I have an operation that should be done by the end of the 5th time step. Am I actually doing it? The temporal logic based assertions will verify that particular feature aspect. Okay. So now we take a small example to illustrate what we have been discussing over the last few slides. Let us say that we have this small toy behavioral description of an application at the input of the architectural synthesis step. So these are 4 operations: E equals to A plus B, G equals to A plus E, F equals to C plus D, and H equals to D plus F. So we see that the input E is dependent on this output of the previous step here. This input F is dependent on the output here. So therefore we can, first we said, what do? We identify the hardware components, resources that we require, and we understand here that we require adders and registers to implement this particular behavioral description. Now this behavioral description then will be scheduled. So this process is scheduling. This shows 2 time steps. So what does it do? So in time step 1, it takes A and B as input and produces E as output, and in time step 2, what happens? This E is taken as input, A is the other input, and G is produced as output. We understand that there is a dependency between these two operations, these 2 addition operations, because this E cannot be used until this output is produced at the previous step. So we have a dependency here. Similarly, we have a dependency at this step. What do we do? So we have these 2 independent inputs C and D, and in the first time step we do the addition operation. The output of the addition operation is this F, and this F is then taken as input in the next time step at this addition, and the next addition operation at the next time step. D is the other input, and H is finally produced as output at the output of the second time step. So we understand that this whole design can be completed in 2 time steps. However, because there are 2 parallel additions in a particular time step, we need at least 2 adder units, 2 adder resources. Now, a particular a sample realization of this scheduled step is obtained here. So this process is called allocation and binding. So we allocate different input data to different registers and different operations to different adders and bind them. So for example, we have used register 1 to store A and register 2 to store B, E, G. So what we have, let us see how we can realize this. At time step 1, we have B and E as input to this adder, and so I will have one mux. So I will have a mux that takes the input to this adder and another one that takes the input to this one. Okay. So then the output of this adder will then go through a demux to register 2. So the demux will enable us to prevent the output from going to R1 and to go to the register R2 as desired. Then what happens? Now we have, at the end of the first time step, we have this E in register R2 and A as previously we have in register R1. Then at the second time step, A and E are driven to adder 1. A and E are driven to adder 1, and then what happens? The output of adder 1 is now G. This G then goes back to the register R2 at the end of time step 2. The same thing happens for the other adder. For the other adder, firstly C and D is the input. At time step 1, C and D are driven to adder 2. The result of addition is F and is driven to register R4 and not to R3 by using a demultiplexer at the output of adder 2. And then what happens is that F and D are then driven at time step 2 to adder 2 again, and the output H is produced, which goes back to R4. So at the end of time step 2, we have G and H in registers R2 and R4, and that correctly implements the behavior that we want to have. So after the architectural synthesis step, after a look at the architectural synthesis step, we will go in deeper into the architectural synthesis step in the next lecture. Now we take a look at what logic synthesis does. So at the logic level, what do we have? We have the register transfer level design. The register transfers, the parallel register transfers at the output of, at the output of the architectural synthesis step. We also have the controller. So we have the FSM of the controller. So this RTL level transfers, the RTL description as well as this FSM has then to be encoded in terms of a Boolean expression, in terms of Boolean equations, and also this FSM we have to do a state encoding, assignment, and realized in terms of a digital circuit. So both the FSM and the RTL description have to be taken, and a corresponding digital circuit has to be made out of that. So at the logic level, the input is in terms of a functional representation. The functional representation is Boolean logic and FSMs. And what is the output? The output is a structural realization through gates and flip-flops. So what we have is called a gate level netlist at the output of the logic synthesis step. So what do we do here? We do the following. We do state encoding, state assignment, formation of Boolean equations, and logic minimization. So at the end of the logic synthesis step, the front end of the logic synthesis step, we have a minimized digital circuit corresponding to the functionality that we have at the beginning of our architectural synthesis step. So that architectural synthesis step at the beginning of the logic synthesis step was transformed into a set of Boolean equations, and those Boolean equations were then realized in terms of gates at the output of the synthesis step, at the front end, at the end of the front end of the logic synthesis step. So here is an example. Let us say we want to implement the function, this following Boolean equation, a plus b into c plus de. So one way is to implement here. So we have two different implementations of the same Boolean equation that we have as input. So if we implement it in the form that we have here, what we have is a direct transformation of this. So a and b, we have an OR gate, and this one we have DE and AND gate. The output then passes through C, and the output of DE we have this OR gate, and finally we have the output at the output of this AND gate. We see that the delay, this is a three stages. There are three stages in this this logic circuit, and the delay of the circuit is 3, and the number of gates required are 4. Now that same function can be implemented as follows. So we have AC. If we just break this up, we will get this, and the same function can be implemented as follows. and we see that there are two stages in this circuit, and so the delay of this circuit is 2. So what we have is a lower delay, is a lower delay realization of this Boolean equation. So both these realizations have the same output and implements the same functionality. However, this implementation has higher delay but lower number of gates, and this one has a lower delay but higher number of gates. We have 5 gates required here. So therefore, the area of this circuit will be higher than the area of this circuit. However, the delay of this circuit will be lower than the delay of this circuit. Hence, we can say that this will be lower in performance but also lower in the area consumed. This will be higher in performance, consuming lower delay, but also higher in terms of area consumed. Right? This is called the micro level optimization of the circuit. We can also do such optimizations at the architectural level, and such optimizations will therefore be called the macro level optimizations of the circuit. For example, if we take this example, we said that this one, for this realization, we require 2 adders. We could easily have done a serialization and done this whole thing using 1 adder in 4 time steps. So if we had just 1 adder, we could do the same thing in 4 time steps. So then obviously it will require lower area, just requiring 1 adder hardware unit. However, it will require 4 time steps to complete the whole operation, and hence it will be lower in performance. So here we also have an area versus delay trade-off. Now we come to the back end of the logic synthesis step. The back end of the logic synthesis step does this. It does the task of transforming the logic model to an interconnection of library cells. This is popularly known as library binding or technology mapping. So it will take you from the gate level design to the transistor level design. Obviously, you can have many different design in terms of the semiconductor technology here, TTL, CMOS, BiCMOS, etc. Also, there can be different design styles here. You can have custom design and semi-custom design, for example. In a custom design, the functional and physical design are all handcrafted. So everything is done by hand, and hence the objective is to optimize every detailed feature of the circuit. Obviously, if the circuit is very complex, it is huge. If it is huge, then such a design is impractical to be done in practice, because it will incur huge design effort and cost. With respect to this, we have semi-custom design. In a semi-custom design, the objective is to restrict the possible circuit primitives choices that we have. Now, we said that in custom design, we can optimize up to the last transistor, right? But in this, you cannot do so. You have a set of pre-computed and designed unit cells of implementation, and that cannot be handled, that cannot be tweaked with by hand, and this restricts the circuit, this restricts the number of choices that you have. But this also gives you the opportunity of handling very large scale designs, and also it also gives you the opportunity of using pre-designed and well characterized primitives, because these cells or primitives that we have here can be optimized with respect to design, because that will be used in all designs. So you can have pre-design, you can pre-design these units, optimize it to the best extent possible, and then use it. So the trade-off is that you cannot optimize with respect to the last transistor possible. However, you can handle much bigger designs, and you can optimize across these primitives. So there are many different examples of custom design. For example, standard cell-based design, array-based design, etc. In standard cell-based design, you have a standard cell. You have a library of standard cells, and you use these cells to design your circuit. To design your circuit and then fabricate. Array-based design, on the other hand, comes prefabricated. It's pre-diffused and pre-wired. So it comes as an array of gates. For example, field programmable gate arrays. So it comes as an array of prefabricated, pre-diffused, pre-wired gates, and you have to program this online to achieve the logic that you want to implement. So how do they do that? They use something called antifuses to short circuit and open circuit appropriate connections between these gate arrays to realize appropriate digital to appropriate functions. After the logic synthesis step, we come to geometrical synthesis. This step is popularly known as physical design. At this step, the circuit blocks are circuit blocks with their real estate requirements. Now what we have is that for each component we have designed it, and we know what is the expected area on the substrate that I will require to implement this block. The circuit blocks with their real estate requirements and their interconnections are specified using graph-like structures. So this netlist, as I said before, are graph-like structures where each node is a component and the edges define connections between components. Edges or hyper edges define connection between components. So we obtain a geometrical layout of the circuit element and interconnection. So this is the behavioral, this is the input to the physical design step, is this structure, this graph-like structure, and the output is what? You have the geometric layout of the circuit elements along with the interconnections as will be obtained on the substrate. So after you have obtained the layout, you actually fabricate this layout on the wafer and obtain the physical chip. It is then the chip is then packaged and then it is ready to market. The chip is then ready to market. Okay. As an example of the physical design step, so let us suppose assume that we have five modules. So the first module has width 1 and height 1. So here we have the modules. We have not specified the interconnections in this very simple example, but we assume that any real example will have interconnection requirements between them. So here we have five modules. Module A has a width of 1 and a height of 1. Module B has a width of 1 and a height of 3. Module C has a width of 1 and a height of 1. Module D has a width of 1, height of 2. Module E has a width of 2 and height of 1. And we have three different layout plans for the same set of modules. Here, see this one, the first one, it has a width of 2 and a height of 1. A has a width of 1, height of 1. C has a width of 1, height of 1. D has a height of 2. We have rotated this and obtained like this. D has this is the height here, basically height of 2 and a width of 1, and B has a height of 3 and a width of 1. Okay, so what we see is that because we have very easily been able to obtain three different floor plans here, primarily because the interconnections are not so stringent here. Obviously, when we have actual connection restrictions, interconnection restrictions, all these different layouts may not be feasible. All these different layouts may not conform to the requirements that I have. Let us say the critical delay that I require between any two connections, the net length, the length between any two components I may require to have bounded by an upper bound. It cannot go beyond a certain limit. because timing restrictions will then be violated. So the signal must pass from, say, module A to module B within 3 time units, but the length of the wire connecting module A and module B that you have, let us say, cannot provide such a timing bound. It requires at least 4 units. So then I have to place it in such a way that the distance between module A and module B is such that the wire length can be reduced, so that the timing specifications can be met. At each step of the design, we also said that this was the design flow in a nutshell. At each step of the design, right from the initial specification to the implementation pre-silicon, we had verification to be done. So we need to verify that the design is correct at each stage of the design, right? So when we are doing a synthesis from a less detailed one to a more detailed one, errors can come up, and we need to verify that there are no errors with respect to the specifications that I have. So there are two main types of verifications that we can have. One is the intent verification, that is checking the equivalence between MLI and BLI at each level. So this is with respect to the figure that we have here. So the figure says that we have an ith level, and then through the synthesis process I come to the jth level. So this is more structural with respect to the ith level. So this is less detailed, this is more detailed. This is more behavioral, this is more structural, because this is a synthesis process in this direction. And in each of these levels, we can have a mathematical or logical model of the specification. So, so at the ith level, I have MLI as the mathematical or logical specification. At level J, I have this MLJ as the mathematical or logical specification. Correspondingly, I will also have a behavioral structural model. This BSI represents the behavioral structural model at the ith level, and BSJ represents the behavioral structural model at the jth level. Okay, and we say that what is intent verification? Intent verification tries to verify that whatever I have at the behavioral structural model at the ith level, does it correctly incorporate all the requirements of the specification that I have? So I will mathematically and logically model the specification, which will incorporate within it all the properties that the design needs to satisfy, and then we will verify that all the properties, all the timing properties, say reliability properties, functional properties, all these properties, are they correct with respect to this mathematical or logical specification. So this is verifying whether whatever I had intended to do is correct. So whether the intent is correct or not. This is the intent verification. As against implementation verification or equivalence checking. What does this tell me? This verification does, what does this do? It is checking the equivalence between MLI and MLJ, or BSI or BSJ at two distinct levels. So is the implementation correct with respect to the two mathematical specifications at the distinct levels? Is the synthesis correct with respect to the behavioral structural specification at two distinct levels? This is verified by checking the equivalence between these two levels, and is called equivalence checking. And we also have testing issues involved at the prototyping level as well as the manufacturing level. So we have prototype testing and manufacturing testing. So prototype testing for design errors. So if I have design errors, the last place to check with respect to driving a set of test vectors and seeing whether all the outputs are correct always under all conditions is by actually driving test vectors through the prototype and finding that over all test vectors, over all test inputs to this circuit, the output of the circuit matches with respect to the expected golden output. So this is called prototype testing. And manufacturing test is to check whether the package chip produced exactly what was designed. So after the fabrication, mass fabrication that we have, we might incorporate errors in the design, right? The number of correct chips that we design, with the percentage of correct chip that we design with respect to the total number of chips manufactured is typically referred to as the yield. So manufacturing test will basically determine what is the yield, means how many are correct chips with after the actual fabrication process and packaging. So manufacturing test checks whether the packaged chip produced exactly what was designed. Now how do you test? You test with respect to certain fault models. For example, you can have stuck at fault models. You check whether certain gate inputs are always stuck at 1 or not. Are they short circuit, always stuck at 1, or are they always stuck at 0? Right? So how do you test that? So these faults are discovered by driving certain test vectors to sensitize these faults. So if I assume that a certain gate input is always at 1, I have to put appropriate test vectors to find out whether the output is wrong. For example, if it is an OR gate and one of the inputs is always stuck at 1, and then if you drive a 0 0 to as test vectors to this OR gate and the output is still a 1, we can understand that one of these input must be stuck at 1. So one of the very important issues in testing is to find out what are the minimum number of test vectors required to uncover a set of faults. We understand that any circuit, any reasonably sized circuit, will have an infinite number of inputs possible, right? So we cannot test a circuit for all possible inputs that are possible. So we have to find out, the research here is to find out the minimum set of test vectors that are essential, that are required, that can sensitize a given number of faults, a given set of faults that we have. And we also have another aspect. The research is also done with respect to design for testability. So in the hardware itself, we have certain extra hardware. We add hardware so that the design becomes more easily testable. And we also have built-in self-test. That means that the chip will automatically test whether certain parts is correctly functioning, and that is called built-in self-test. With this, we come to the module 3 and the last module of lecture 1.